Alright, I just wanted to make a short lecture about momentum, which is what the next unit is about. Well, actually, this is going to be momentum, impulse, and the impulse-momentum theorem. Alright, momentum is represented by a lowercase p. And because momentum is a vector, we like to give it a vector hat sometimes. So, because it's a vector, it has the sign. And the sign is going to be the same as the sign on velocity, because P is equal to mass times velocity. So whichever way the velocity points, since this is a vector, momentum is a vector, and whichever way the velocity points, the momentum points. So the momentum can be positive or negative. All right, so there's our first formula. Another quality I want to talk about is impulse, and impulse is J, and impulse is also a vector. But I guess a couple more things to say about momentum is that when an object has a mass, right, and is moving, it has momentum. And that's kind of the idea behind momentum. Units here for momentum are kilograms times meters per second for velocity. And there are no special units like newtons or joules or watts or whatever for this. You just have to say it every time. It's kind of a mouthful to say, but kilograms, meters per second for our units of momentum. All right, then there's another quality we got to know about, which is impulse, and impulse is equal to force times time. We've never really talked about how a force can be applied over a different length of time, and there's going to be a relationship here between impulse, which is also a vector, because force is a vector and can be positive or negative. Time is not a vector. But we're going to have a relationship between these two formulas that I'm going to show you in a second. Units here on impulse are going to equal units for force, which are newtons, times units for time, which are seconds. Now, although these two might look different, these two, they're not. If we remember that, so what I'm trying to say here is that Newton seconds, I guess I can write it over here, that kilograms meters per second is the same as Newton seconds. And the reason for that would be that a Newton is a, what is a Newton? A Newton is an F equals ma, right, is a Newton, and that is a mass, which is kilograms, times an acceleration, which is meters per second squared. And so what we have here, if I just take that and plug it in right there, whoops, forgot the G, kilograms meters per second squared times seconds, and you can see that that is going to allow me to cancel a second off the top and the bottom. So what I'm left with there is then this, right, which is the same as the units for momentum, which are kilograms meters per second. So what we're saying then is these two are equal. So anytime we see kilograms meters per second or Newton seconds, they're the same thing. Generally, we stick with Newton seconds for impulse and momentum, kilograms meters per second, but the two are related, and that's important to see. Okay, so I'm going to show you another formula here, and before I do that though, I guess one more thing about impulse. We can think about impulse maybe with a trampoline example. If you were to jump on a trampoline, and we know, if I was to draw a trampoline, when you maybe you jump up in the air and you are then going to fall maybe 4 feet, that normally this would be quite a jump, right, to make, if there was not a trampoline beneath you. But when there's a trampoline beneath you, that this length of time that the force acts over is longer. And so there's kind of this idea then that you're going to undergo a change in momentum, right? And by changing the time period, that the force will be smaller. And so what I'm saying is there is a relationship here between a change in momentum and an impulse. Where can we see that, or how can we see that? There's 2 ways for me to show you. I guess I can try and show you this way first. I'll start by writing Newton's second law. F equals ma. And Newton's second law, we can then think of it as F equals m. Do you remember the formula for acceleration? That was a long time ago, but I wonder if you remember. This is a vector. This is a vector. Okay, it was change in velocity divided by the change in time, which I'm just going to use t. So, all right. So this is this is still Newton's second law then, written this way. All right, let me multiply both sides by time. I think you can start to see where this is going. And delta V, if you remember, is the same as VF minus VI. So I'm going to go ahead and rewrite it one more time. Right? Oof. All right, and this is called the impulse momentum theorem. I just put a hyphen right there. I think there is one. I can't remember. Impulse momentum theorem. And this relates the 2 ideas from before. Let's look at why. If I come back to this formula, this right here is just mass times final velocity. So I could think of that as being PF. And I could think of this then as being PI. And then finally, I can rewrite F times T as J, right? And I can rewrite this as what? What's PF minus PI? You remember? When we have a final minus initial, we can say it's delta momentum. All right, so what we're seeing then is that the impulse momentum theorem, right, is telling us that impulse is equal to a change in momentum. And it's not a new formula. So here, when I wrote this, you're like, oh, that's a new formula. No, it really isn't, right? Because where did this come from? It came from Newton's second law. So here we're going to write Newton's second law, right, this way, and call it the impulse momentum theorem. But also realizing that what we're saying here is that impulse is a change in momentum. F times T is mvf minus mvi, and that's our connection between the 2. So that's what we're going to end up using here quite a bit on the practice, and to draw this relationship between impulse, or J, and momentum, or P. All right, that's about it, and I'll talk about conservation momentum next time, and let me know if you have any questions. All right.